Okay. Starting up early, but hopefully I should see the live thing pop up soon. Should be live. Okay, good. Okay, so I've confirmed that I'm live. That's definitely good. I am gonna set up shop, like need to close a window and stuff like that. But we're gonna get started in a bit. Everyone who's here already, feel free to say hi in the chat, and we're gonna get started quickly. Okie dokie. All that stuff seems set up. Let's make sure the tablet also works. That should be good. Nice. Cool. Then I'll wait for a few more minutes before we actually get started, but I figured I might explain the setup a bit. I have been suffering from a bit of RSI symptoms, so I made a bit of an investment into some proper gear. People might have seen some of the pictures on Reddit or Twitter. But then some of my colleagues agreed it might actually be fun to also kind of show the gear as I'm typing along. So we're going to give that a spin. We're going to try it out, see if it makes it kind of cool, interesting, because I can also imagine it makes it a bit less magic if you can actually see me doodle on my drawing device. So that's the whole story with the setup. You should be able to see my hands move and that sort of a thing. Hopefully it's not going to be too distracting, and if it is, we're going to not repeat it, but that does hopefully explain the hand and the keyboard and the setup and everything. We are not quite at time just yet, but again, if people are dialing in from anywhere, do let me know. I always think it's kind of fun to know where people are sort of dialing in from. Oh, yes, I can sort of zoom a bit here. See if the entire notebook ran. Yes, it seems that it did. Okay, we're gonna have some fun demos in a bit. But still 2 minutes. Okay. But okay, I think we can sort of get started then, because it does seem that there are a couple of folks trickling in. Yeah, so starting up a little bit early is not necessarily a bad thing. So today what I'm going to be talking about is two-dimensionality reduction techniques. And what I'll also just go ahead and do is just pop up the whiteboard there. So the whole story here is that very often you have a data set X, and this data set X might have a lot of dimensions in it. So, you know, it might be the super duper, what I will call wide array. And sometimes that's fine, but there can be reasons to maybe reduce that down. So what people like to do is they like to call a dimensionality reduction technique. And that will transform the original data that we had into something that is a lot smaller. This would typically be a bit more thin, so to say. And there are a couple of reasons why people are typically interested in this. For starters, if people like to make visuals, typically two-dimensional charts kind of work. So sometimes if you want to visualize a big data set, it can make sense to maybe reduce it down to 2 dimensions. Maybe some of the clusters that were in the original data set can still survive. That might be a reason to reduce it down. Another reason might actually be machine learning. If you do the reduction in a clever way, that you remove dimensions that don't carry any information, you might still be able to capture most of the information of your original data set. But you might be able to throw away some noise, and that is something that can be seen as a, what's the right word here? Like a generalization. No, that's not the right word. What is it? The idea, the main idea is you're going to throw away regularization. That's the word. This can be seen as a regularization technique. The main thinking here, of course, is that by having less features, the odds of a machine learning algorithm overfitting on one such feature might also be reduced. A lot of it depends on how you do this reduction, though. And if I look around at the notebooks and what people are doing, then it seems that there are two approaches that are just simply the most popular. One approach is called PCA, and the other one is called UMAP. Typically, PCA is easiest to explain. Typically, UMAP is the hardest to explain. But what I figured I might do in this sort of live coding session is instead of going too deep into like the math and how both of these two items work, I figured I might go like way deeper into the intuition. What I can probably do is come up with a couple of interesting examples that really highlight how PCA and UMAP just go about this reduction differently. And hopefully that'll also help you in deciding when both of these techniques may or may not be appropriate. So that is the thing that I mainly hope to focus on today. What I've done is I've collected a few data sets, and we're just going to have a look at how different of these techniques cause different reductions, so to say. And yes, the notebook that you're looking at right now will be shared on the YouTube appendix playlist, GitHub repo on the probable GitHub account. So all the code that you're looking at here is definitely something you can inspect later. So I was wondering, like, what might be a good first place to start? Like, what might be a fun data set to play around with? And then, like, upon inspection, it turns out that scikit-learn has this make Swiss roll dataset generating function. Scikit-learn has a bunch of them. They're used all over the docs. But I thought this was kind of an interesting sort of visual, if you will. This is a three-dimensional picture. And you can see that it's kind of like at the epicenter of it all, there's kind of this swirl. Like that's the main thing that is on sort of this front plane over here. It's just a bit of a swirl. And then in this direction, that swirl is really just being kept intact. There's not really a pattern besides a uniform distribution going into this direction over here. But already, kind of as a sort of testing ground, you can kind of wonder, well, this is interesting because this is 3D. This is a three-dimensional picture. And you can kind of wonder what might be the best way to turn that into a two-dimensional representation. And before diving into like what UMAP does and what maybe PCA would do, it is a good idea to just think for yourself, like, hey, what might be reasonable here? Because obviously it would depend on the use case, but just a few themes that might matter here, right? You could argue that it is really good that these axes that we've got over here, that those are somewhat in the same scale. This axis, if I look at the minimum and maximum, that spans about a distance of 20. If I look at this one over here, that also seems to be about 20. It does seem that this axis is a bit bigger, 25, but they're roughly the same distance, so to say. And that's usually a good thing. Like you can imagine turning something from a 3D representation into a 2D, you wouldn't want that to be overfitting on a single axis. So it's definitely a cool thing that this is here. But then if I start thinking like, what's the main pattern? And of course, the colors that I've added to the chart over here, that really does help the influence. But one thing that I can at least argue is if there's really a main pattern in terms of like the structure and something that is different, there's really just a uniform distribution on this side. Like this is really just a sort of random spread in this direction. The real pattern that we have in this picture is this spiral over here. Like that's, I think, a somewhat unique property, if you would. But there is also an interesting thing when we think about distance. So there's a reason why the colors are in this way. What I could do is I could just pluck a couple of points. Like I could pluck a couple of points that are over here, like on the very much on the edge of the blue space over here. And I can pluck a few points on the yellow space over here. And very naturally, you could just go ahead and observe the distance between these points is relatively small. At least in the 3D space, you can definitely argue that. What's a very interesting question is, do we want this distance to be useful and be represented in our 2D representation? Or do we maybe care more about the distance on this spiral instead? Because if I care about the spiral, then the distance between this blue dot and this yellow one doesn't really matter. What matters more is the distance from this blue dot and its neighbors. So that's an interesting thing to think about. Like, do we care about the global structure? Is that a thing we want to try to keep intact? Or do we care more about the local neighbors? There's a bit of a conundrum between those two. The link to the repo, I'm seeing questions pop up. The link to the repo will be in the show notes once this thing is recorded and out there. But, I mean, I guess there's no harm in showing that real quick. In general, all the content that I make for all the videos, right shortcut, can be found on the YouTube dash appendix. Okay. GitHub.com probable AI /YouTube appendix. There we go. All the live stream stuff typically goes in here. So if you go to probable-AI, you go to YouTube appendix, you are going to find like all the notebooks that I've made for pretty much every video, and they're always typically going to go here. So probable-AI /YouTube appendix. That's where you're going to find the good stuff. But anyway, coming back to this, like I hope that we agree that there's something interesting about this data set in the sense that points that are close together, like in 3D space, and again, a point over here and a point over here, that is close together in 3D space. A point over here and a point over here, again, that's close together in 3D space, but is that really the distance measure that we're most interested in? I do think that that's like an interesting question. Let's remove that. So for starters, I figured what would happen if we throw this into PCA. So I wrote a little bit of code that does that. I'm going about it relatively straightforward. I have a PCA estimator over here, and I come to think of it, let's just zoom in a smidge. So I've got a PCA estimator over here. I'm saying let's just do two components. I'm going to take the data points that we start out with. So this is the wide data set. This is the thin data set, so to say. But then as a first visualization, I figured I might do something interesting, which is I'm going to call the inverse transform function. And that's going to help us explain what PCA does. So what the inverse transform does is I have my wide matrix, right? The stuff on top here with the PCA, that's going to turn it into a thin representation. But then what I'm going to do is I'm going to try to reproduce the matrix from this one. I'm going to lose a little bit of information by doing this, but hopefully the information I lose is... oh, wait. I need to actually... you can't see what I just drew. But anyway, let's just draw it here then. From the thin matrix, what I'm going to do is I'm going to try to make the reproduced matrix. But the whole point is that from this thin matrix, can I generate the original data set in such a way that not too much information is lost? Like that's a very interesting way to sort of maybe learn more about the PCA. And that's what you're going to see below here. So this is the reproduced data set. If I take the wide data array, turn it into something thin with PCA, and then make it big again, then this is the shape that comes out. Like this is what the spiral will look like after PCA tries to reproduce it. And just for good measure, this is what the original shape looked like, and this is what the shape looks like afterwards. So one thing that we can very clearly see is that like the spiral shape, that is definitely kept intact. The only downside is that this is a 2D image of a 3D representation, so to really see what's going on here, I figured I might also just install Plotly. And I think I should be able to, let's just rerun this actually. Like if I have Plotly, it's a little bit easier to show what is happening in 3D. But if I use PCA and I try to reconstruct it and I just have a look around as what's happening, then you are going to notice it is really just a flat spiral that comes out. All the 3D information seems to have been lost. So if I think about what PCA is really doing here, PCA is basically looking at this, and it's sort of thinking like there's some sort of slice that I can do in 2D. Maybe the slice is precisely on this plane over here. And if it just so happens that in these two directions I can really fit the most variance, then that's the slice of information that I'm going to store everything in. And if I were to ever try to go back to 3D, you can hopefully also imagine that that third dimension information is basically lost in this particular case, because in this direction there's no information. It's all just uniform. So that just gets forgotten, so to say. But it is pretty interesting to see that we do get the spiral shape out. Like, that is definitely kind of cool. In particular, if you were to plot the 2D information, right, like this is the two-dimensional representation out of PCA, then you definitely very clearly see that the spiral shape, that's the thing that it's picked up. Like, that's the pattern that it has, and that's the thing that's really been kept intact. But you still get this weird phenomenon, right? Like the points, if I were to do like a similarity thing in 2D space now, you are going to get this odd thing where what are the closest points to this green dot over here? Well, there's lots of these blue dots over here that are closer to this green dot than other green dots are. So this is very much still I would argue, a global space compression thing. We're looking at the global picture, and we're trying to have things that are distant from each other in the larger space also be distant from each other in the smaller space. So that we're trying to keep the global thing intact. We're not really doing anything with local information. And that's also where, if I were to try to explain the difference, in my opinion, that's also where UMAP is the other way around. In UMAP land, we are not trying to really focus in on the global picture and try to keep the global distances intact. No, UMAP really likes to look at the local thing that's happening. So we're going to repeat the same exercise. I'm doing the same thing now, but with UMAP. So I'm trying to reconstruct the picture using UMAP. And this is, of course, a picture in 3D space. It's kind of 2D. So instead, what I might also do is try to look at the same picture in 3D. And just from the outset, like, you can look at this and you can kind of go, well, this looks a bit weird, right? Like, it's the spiral information seems to be lost. So it might feel like the PCA is doing something a bit more clever there. But then if I were to look at the 2D representation of UMAP, right? Like, this is the output of UMAP. Then it really does seem to cluster some stuff together. And you can also like see that there's not really a homogeneous sort of distribution happening here. Like, things really clump together, so to say. But there is an interesting thing happening. So let's put all of that stuff like side by side. So in the 2D representation, again, this is PCA, right? And this is UMAP. But if I were to look at the weird thing of PCA, then it would definitely be in the realm of, hey, there's a bunch of points here, and there's a bunch of points here, and those are really, really close together. But if I think about distance on the spiral, points over here should really not be similar to points over here. But because PCA wants to keep the global information intact, there's no other way to put these points. If you were then to look at what PCA, or sort of what UMAP is doing on the sort of other end, then sort of the notion of global distance is kind of really thrown out the door. But you do see that all the points that are close together locally, they remain close together in this space. It kind of feels like we're drawing a single strip, and that all the colors in the strip are close together as where you would expect. So that weird phenomenon where, hey, the green dots over here are very similar to the blue dots, that kind of gets forgotten here. And depending on what you're doing, that might be a good thing. UMAP is really good at keeping like, if your data set has clusters, UMAP is really good at keeping clusters intact from your original data. And it does that by kind of throwing away this whole idea of keeping the global distances in line. PCA, on the other hand, really is more of a measure where we look at the total distance and the total information, and that's what we optimize for. But then if there's local clusters, then we don't really care about that. We care about the total variance, and that's what PCA tries to optimize for. So that's a pretty interesting way to think about it. And to me, at least, I feel like the spiral data set does a pretty okay job of showing at least a subtle difference between the two methods. I'm also keeping an eye on the chat, and people are saying that they're getting hungry. It is lunchtime. Feel free to make a sandwich. Like, don't let me block you from getting a sandwich. But what I do hope, at least, if for this little introduction, that there's a little bit of an interesting difference happening here. Like, what do we see in PCA land? Keeps the global thing intact. What do we see in UMAP land? Throws away the global thing in favor of keeping these local clusters. And you also kind of see as a side effect of that it really tries to follow the spiral a bit more in a way that these points that necessarily shouldn't have like a similarity are also not necessarily close together. Like that's I think a nice thing about the UMAP. If I were to grab a random point over here, and if I were to say, hey, what are your closest neighbors? You can argue that follows the spiral path a lot more clearly than stuff you see happen here. Like another example, like everything where points can be shared across the spiral, you can kind of have that argument, so to say. So if there's any questions about this, I would like to move on now to a more tangible example. But what I mainly hope is that as an introduction, it is clear that PCA and UMAP just do kind of fundamentally different things. But it seems like no questions are coming in yet. I'll just give it like another minute. But yeah, seems pretty good. So, okay. The example we just did is relatively theoretical and perhaps also not even the most practical. I mean, after all, we are taking this Swiss roll shape, which probably doesn't represent something we'd see in real life. And then we will also have this be turned into a 2D thing. And, you know, usually you're not interested in a 3D thing becoming a 2D thing. Usually you're a bit more interested in like a 300-dimensional thing becoming a 2-dimensional thing for visualization. Like that's the more typical use case. Magda is pointing out, by the way, that the creator of UMAP, Leland McInnes, he will be speaking at PyData Amsterdam. That is indeed a astute observation. I'm very much looking forward to his talk. I'm also speaking at PyData Amsterdam, by the way, in case people are interested. Also, if people are interested, one of my favorite interviews for the Sample Space podcast was with Leland as well. So if you haven't already, definitely check out the Sample Space podcast. The creator of UMAP was in one of the interviews there, and it was definitely a great show. Anyway, coming back to this little phenomenon. Typically, what people like to do when it comes to visualization, at least, is people like to look at something like embeddings. Like that is typically the numero uno use case these days. So what people really like to do is they like to look at a thing that has like 300 dimensions or more, and then they're interested in understanding if there are clusters in it. And then it can suddenly become kind of a nice idea to turn that into something two-dimensional. And again, I need to remember that when I'm drawing something on screen, that my face can be in the way, so I'll redraw. So we're going to go from 300 dimensions to 2 dimensions, and we're going to do that on embeddings. But the main thing I want to go towards here is what we're hoping in this 2D chart. Like, when is a 2D chart useful to us? Well, typically it is useful if it's very easy to spot clusters in this space that are still intact in this space. Like, that's the main thing we are interested in doing. And if that's the case, we can kind of wonder, well, which of these two methods might we prefer? So I can come up with two arguments here. Like, one thing that UMAP does really well is it does keep sort of clusters together. And you can definitely see it even starts clustering things together even when the data was kind of uniform. So you can kind of argue like, hey, maybe that UMAP stuff is really, really great at doing the clustering thing. Like if clusters appear in the UMAP chart, maybe that says something about the 300-dimensional situation as well. The only thing to be aware of, if that's your reasoning, is that you can also get clusters where there are none. And this picture also does a pretty good job at showing that. So, for example, we know that the spiral data set is perfectly uniform. Like all the data points really do touch each other. So you could wonder, shouldn't this just be one big cluster then? But you do see, if you look at the UMAP chart, that there are like distinct islands that could be selected, so to say. And there's also a little bit of danger there. It might be the case that there are no clusters in the higher dimensional data set, but that you do start to see them in the UMAP space and that you therefore start to assume that they really do exist. PCA is a little bit less PCA has this issue way less, but the odds of a cluster appearing in PCA land are a lot smaller. And I really was looking for a way to explain that, and that will bring me to some interactive tools that I made for the notebook that hopefully do a pretty okay job at explaining just that. So, we are going to have a look at a data set. The data set is a data set I found on Kaggle. It has some customer support tweets for a UK supermarket. So these are just things that people have said on Twitter about a supermarket. I have a data frame, and there's like support questions in them. And we can have a quick look. It's not necessarily like the most artful language, of course, because it is all social media text. Did I not? Oh, I might have ran. Yeah, I ran another cell, but yeah. So the supermarket in question in this case is Tesco, and people are just asking all sorts of questions about it. That's basically what's in there. And it's about 16,000 of these remarks. So the data set's not necessarily small. It's pretty big. So going through this entire data set manually would not necessarily be a great experience. Lucky for us, we have tools available to us like sentence transformers, and this is a component that uses sentence transformers in a scikit-learn fashion. I can have an encoder. I can then give text to that encoder. Out comes this big wide array. I could be wrong. Like it was 300 something, if I'm not mistaken. Yeah, so 380 dimensions. That's kind of the shape of the thing that we're dealing with. So, pretty wide. What we're then going to do is we're going to have PCA and we're going to have UMAP, reduce it down to 2 dimensions. And then we're going to be using this base text explorer widget from the bulk library, which is a library that I maintain. But we are going to just explore the data set by doing this. And let's just kind of zoom in here. Whoops. This is the data set in 2 dimensions when I run PCA. So, it's fine. It's kind of interesting and useful, but it seems to be one big blob when I do the PCA thing. If I were to scroll down now, and if I were to look at the UMAP thing instead, then it's still kind of a blob, but you can also definitely see that there are these clusters. And what we're of course going to be hoping for is that these are the clusters that will also matter. But maybe the easiest way to explore these clusters is to also just highlight a few data points, which this tool makes pretty easy to do. So I can keep my mouse cursor pressed down. That'll activate the selection tool, and I can just make a selection in this space, so to say. So looking at this little cluster over here, it seems to be a checkout machines not dispensing change. Something about £1 coins. So this seems to be about coins and stuff, and currency, and you name it. Note, by the way, that there is this resample button that I can press. There will always be like 10 items being visualized over here. This cluster has more than 10 examples, so if you want to keep on sampling from the selection, then this is a thing that you can do. But a somewhat more interesting thing that you can also do is just type some text in here. So I can do something like, my food does not taste good, something like that. And then the cool thing is that the points actually get a bit of a color. So depending on the cosine similarity in the original data space, I'm going to embed this bit of text, and then I'm going to compare it to all the text embeddings that in the white space, and if there's like a good similarity, then lights pop up. So you can actually see like, hey, the people complaining about food not tasting well, that's in certain regions. I happen to know this one thing. Apparently in this time period, you could get Call of Duty for like cheap at Tesco. So if I type Call of Duty, then there's a very specific cluster over here that lights up. It's kind of a nice little example. So I can make that selection. And then you can see that it's about PlayStation 4s. There's Call of Duty, like abbreviations. There's Nintendo Switch, so I guess like another thing that I could also do is if I deselect that is I could talk about video games, Super Mario, Call of Duty, right? Okay, so I could bring up all sorts of video game terms. The same cluster would kind of light up. But this is like a cool thing that UMAP does. Like UMAP is pretty good at sort of putting stuff that's actually supposed to be in a cluster in a single uniform cluster. And what I could now do is I could sort of go back up and I could go to the PCA thing. And if I were now to type Call of Duty, Mario, Nintendo Switch, something like that, then I can definitely kind of zoom in and I can see that in this corner, in this realm, there is something happening with video games, but it's definitely less of a pronounced cluster compared to what I've got down below here. And to me, that is definitely something that makes UMAP kind of unique. There's something about UMAP where clusters in the original data can definitely remain intact, even though like the global distance is being thrown out the window. Like UMAP is really looking for the local information. I think this is kind of like a nice example of that. Another thing, though, that might be interesting, what's another typical complaint? I think late delivery. Yeah, so like one thing that I do like about the PCA thing is it does seem that, hey, if I'm interested in like late deliveries, which is a very, very common complaint, then it does seem like a pretty big chunk over here does light up. So one thing that is definitely kind of cool here is like, oh, actually, this is maybe somewhat of a larger topic. A lot of people talk about late deliveries. And the PCA is actually telling me that, oh, that might actually be kind of a global thing if I look at like all the text that I've got in this data set. And if I were to try to do that over here, something like late delivery, then you kind of also see like a big cluster light up over here. But you don't necessarily get the interpretation that the cluster that we have over here might actually be so important that it has something global. And this is like the subtle thing that PCA is able to tell you that I think UMAP it's harder to assume something like that. Again, because PCA really tries to do the global thing and UMAP really tries to do the local thing. And here we kind of have to talk about like what's the intended use case a little bit. So if you are interested in doing some data annotation, so let's say I'm starting out with a classification use case and I'm not interested in using LLMs, then I want to label some data. And let's say I want to have a class that's going to tell me, oh, this complaint is about deliveries or something like that. Well, then you might be interested in just saying, well, I'm only interested in looking at examples where it might be pretty clear that it's about delivery first. That's reasonable. And then you could wonder, do you want to maybe sample from this subset done with PCA? Or are you perhaps more interested in grabbing something over here using UMAP, where you're really just going to try to focus in on this one little cluster over here? The answer is you probably want to do both. The thinking is that you are probably going to be able to get lots of examples from this cluster that are really all about deliveries, because the clusters in UMAP space are just a little bit more precise. However, one could certainly argue that if you're interested in building a classifier and you're interested in having a data set that also has negative examples, then you do want to have examples that are somewhat similar to being about a late delivery, but also just different enough. And then you can definitely imagine there's still a whole chunk over here that would not be interesting. Like you probably don't even have to look at these examples. But by being able to grab examples from like this pretty wide an open space, you're probably also going to get a bunch of negative examples that are good to have in your train set as well, that you might not be able to grab if you're really being zooming in and focusing in on a cluster that's bound to have only delivery complaints, so to say. So hopefully this demo was kind of interesting. If people are interested in this, by the way, I'm working on a new, I've had the library for a while, but the library is called Bulk, and I'm interested in adding more of these high-performant sort of 2D representation exploration utilities. So this base text explorer is something you can download now and sort of play with. It is all pretty alpha. I want to make some changes to it. But I did think it was kind of a nice point in time to also put this in a demo, at least for this use case. Because I do like to think that if you're able to play with the data a bit more easily in a notebook, then also the intuition is also a lot easier to grasp. Someone is asking a great question at this point. So Aka Excel is asking, how do they deal with outliers, UMAP and PCA? I mean, it does depend on the definition of an outlier, but one thing you can see over here, at least, PCA, it really has to reduce everything down. So, you know, there's a couple of outliers still in this 2D space, but if I were to look at the text over here, it doesn't really occur like something really, really crazy is popping up. One thing I would also maybe say is, like, when is something an outlier is also almost a philosophical discussion. So the Call of Duty thing, right? This is a Tesco supermarket, and at some point, people are talking about Call of Duty. Like, when is something a cluster and when is something an outlier? I mean, it is all text-based stuff, right? I would be able to imagine if you have like 300 dimensions and you got to reduce that down with a linear model, then you're usually only going to get like one big blob anyway. I can imagine if there's a single dot here in PCA space that I would deem that more likely to be an outlier, sorry, in UMAP space. Yeah, like these two outliers seem to be a bit more about a specific place that doesn't happen too often. Plastic bags, pool noodles, very specific product. Yeah, I think the answer is it's just always going to be depending. I don't know if I have anything very general that I could say about outliers, because outliers tend to be a bit of a can of worms as well. My gut feeling would be that PCA typically likes to make a big single blob out of everything, and that UMAP therefore might be a little bit better suited to find outliers. But your mileage will probably vary a lot. This will be a great point in time to maybe check if people have like requests. Like I can throw some stuff in here and sort of play with it for a bit. I'm kind of curious if people have questions between the difference of PCA and UMAP. But what I am hoping at this point in time is that at least some of that intuition and how UMAP is different than PCA, that does sort of come across by exposing ourselves to this example. I'm actually also kind of curious what this cluster might be. Just have a look. All right, this is something about, so the topic here is that something seems to take a long time before it's done. So that makes sense. That's kind of a cluster. There's people not being very grateful. Okay, if I do something like this takes way too long, hours, minutes. Yeah, so the cluster I had over there that was complaining a lot, definitely. And if I add delivery, yeah, okay, so delivery is sort of over there. I think there was another cluster where the website is broken. Like that was also something people, yeah, so there's a there's a website cluster over here as well that I thought was kind of interesting. We can always also have a look at like, hey, what's happening over here? Is this about something? Oh, that's interesting. This is all about like something vegan. It is all about ingredients and diets. That's actually kind of interesting. What I really like about this interface, by the way, is it really does invite you to just select something and then to confirm your intuition by also typing something. That's something I really like about building this. But yeah. Swiss roll, someone is asking. What is a Swiss roll? I feel like I should. Is it like a? Okay, that's a bit of. That does look tasty. Okay. Interesting. So I see something really, really light up over here. So I'm just gonna highlight that. This is probably something. Yeah, this is about being halal, so that's not like this is Tesco in the UK, so I can definitely imagine that Swiss rolls might not actually appear in this data set so much. What's probably happening here, by the way, it could be that Swiss roll doesn't map onto anything in this data set, and there's just a few like there's a bit of noise over here, which is why this number is a bit more yellow, or this dot is a bit more yellow. But really, maybe what's happening here is that nothing is really matching. So maybe I should add like a threshold where if it's not above a threshold, you just always put to 0. I could do something like meat. That's definitely there. And what if I do something like water or drink or expensive? Yeah, you do see different regions pop up, so that's definitely still kind of cute. Right. So there's a very interesting question. Like, if skills do not match, you typically standardize before PCA. Is that recommended for UMAP also? I'm going to attempt a bit of reasoning here by going to mention a extreme example. Suppose that I've got like 3 axes over here, and this is 0, right? And then on this axis, the maximum value is 1. And then on this axis, the maximum value is 1. But then on this axis, the maximum value is like 600 million, billion, gazillion, some sort of huge, ridiculous number. Then for a lot of algorithms, this would be a problem, right? Because, boy, this scale is a lot bigger than this scale. So all your nearest neighbor kind of tricks would totally break here, would totally overfit in this one axis. But then there is a thing you can do to maybe remedy this, or actually... Now, I do think it's safe to say that it's almost always good to have like some sort of numeric balance. Like if you have 2 distances and one distance is in kilometers and the other one is in meters, like that's usually never a great idea. Like to see if you can maybe standardize that. But one thing that is a bit subtle inside a UMAP, if I I should really read up on the algorithm. I'm doing this from memory from like 4 years ago when I last read it. But there is a notion of making a graph of nearest neighbors, so to say. And yeah, actually, if once you construct a graph of nearest neighbors, this is also definitely still a concern. So I think in layman's terms, always just try to attempt some sort of thing that prevents this ridiculous thing from happening. That's the general rule. But yeah, I think that's yeah, that's I think the most simple thing that's always true that I can tell. I haven't benchmarked this though. Like it would be kind of a fun little Saturday experiment to see if you can break UMAP by just doing something silly with the axes. If there's time, I am able to do that in a bit actually. But I want to make sure all the other questions, like my demos need to be done and questions need to be answered, but then we can try that. Like I can make one of the axes like ridiculously big and see what the effect is. Yeah, and so someone is commenting like, "Hey, Vincent, some of the clusters here that you that we're looking at, like sometimes, like if I just look at the delivery again, like there seems to be like a little subcluster over here, but at the same time, this cluster over here is distinct from the cluster over there. Is that because UMAP is doing something silly, or is that because of the data? That's always something you can only tell by inspecting. So that's a pretty good comment. But one thing I do think is fair to say, like this is definitely still about deliveries, but it seems here that the complaints are mainly about the driver. And there's also compliments about the driver, by the way. Like in fairness, Tesco also has great people working there. And here, it's more about delivery itself. So when does delivery get here? My thing is late, that sort of a thing. So even though like I really need the color to help me figure out this cluster over here, is but yeah, like UMAP will tell you where the clusters might be, and that will help you sort of inspect further. But you do need to do that sort of manual effort yourself. Like UMAP is really good at asking. UMAP is really great at forcing you to think about great follow-up questions. It is not great at answering all the questions you've got immediately. Again, check the interview I did with Leland. He has a couple of really good quotes on this. Someone's asking, is it possible to highlight the UMAP points, but also be highlighted in PCA space and vice versa? Well, I'm happy you asked. So this is an old open source project of mine. It's not the most speedy, but what I am able to do here is I should be able to make a selection. Let's select something from UMAP space over here. And then you do see that like a certain region in UMAP, in PCA space also lights up. So we do see that there's this one cluster over here that seems to correlate. And if we were to move this a little bit more to the cluster over here, it's different. Cluster over here, it's a bit different. So, you do see that there are definitely sort of still clusters in the PCA space, but you can also see that sometimes the cluster really just spans the entire blob as well. So that, to me at least, that has always made it a bit easier for me to just pick a cluster in UMAP space and sort of work from there. I can also do it the other way around, by the way. But you do see that there's also a bit of a correlation. Like there's still something of a general distance happening in UMAP space over here. And this was all about placing orders and people waiting, I think. And, there's still some general information being saved. And it's also my goal to have a feature like this, what you're seeing here, using this faster engine. Like the engine here for selection is way faster than what I'm using below. But I have also made in the past this package called ClueStar that allows you to compare two UMAP charts or a PCA chart with a UMAP chart. So, this is pretty cool. It's a nice little demo. Be careful about like assigning too much value to shining demos though. Like it is a very shiny demo and it's really cool. The most important thing though is at some point you just make a selection and you just have a look at the text that's in there. And maybe double down on that instead. But anyway, this is the final quick demo I wanted to give. Like, the main point I hope to get across here is sometimes you don't have to worry too much about the math and like the implementation of these machine learning systems. Sometimes it's just a whole lot better to make great tools to help you visualize and gain an intuition. And that's what I'm trying to do here. Hopefully these demos were interesting enough that you also consider, oh yeah, like UMAP might be good for some sorts of clustering and it really tries to do a local thing and you name it. But I do want to also highlight that PCA is also pretty good at just being the regularizer. Like it tries to keep the global information intact. And if you're interested in doing this for machine learning, then maybe it's fine not to do it to 2 dimensions. Maybe it's fine to get it to 100 dimensions instead of 400. And then that reduced representation might be better against overfitting in your machine learning pipeline, etc. But yeah, I think all those points have been made. The thing I want to do now, simply because I do think it's a great question, is I want to zoom in on that question about like standardizing. So we remember what this looked like, right? Like this looked pretty okay. But what I'm now going to do is I'm just going to mess up the data a bit. I'm just going to do some tomfoolery. So this is the X array. And I'm just going to take that first column. And I think I am allowed to do this. Right, like I'm allowed to just take that column and I'm allowed to say like, let's just multiply that by 5,000. And then if we have a look at that first guy once more, yeah, then these are like to the power of, like we see numbers to the power of 1, to the power of 2, etc. And if I were to take the next column, right, column 1, then we get to the power -2. So that's like way smaller numbers. So, okay, we just kind of quote unquote poisoned X. Let's see what happens when we now throw it into PCA and UMAP. And something's going to tell me that the charts might be just a little bit different. I do want to check the documentation actually, because I think PCA standard scalar. Okay, PCA docs scikit-learn. There we go. Yeah, so yeah, there we go. So the the input data is centered but not scaled. There you go. So the scaling, yeah, so PCA, the implementation, does assume that it's been scaled beforehand, I think. But yeah, okay. We just trained PCA and we just trained UMAP again. So this was before. Let's look at it after. Oh, this is so funny. So you can see that it zooms in very well. It's just a really, really thin line, right? So PCA is completely overfitting on that one axis that we just added because it's really just a straight line now. And I can make a selection if we really wanted. And we can also do a bit of typing here. So we could do something like, hey, something about a delivery. But yeah, like it's really, really overfitting on one dimension now. So that's okay. That's kind of a cool demo. What happens if we do UMAP? So again, this is before. Let's see what happens after. It's, I could be wrong, but it looks roughly the same. That is interesting. If I do the delivery, yeah, it's exactly the same. Huh. I am now super curious. UMAP scale. I did not expect that. I will need to dive. I kind of want to dive into this one. Did not expect that. So standard scale is anything in the docs about scaling UMAP? There is something in the API. No, that's not what we're interested in. Just the UMAP class. Does that maybe tell us something interesting? So we have number of neighbors. Yeah, so it is doing a nearest neighbor thing initially. Yeah, okay, this is a hypothesis. So this is not Vincent doing a proof. This is Vincent sort of just thinking out loud. But, okay, the big data input that I've got, X, we have the first column, this one over here. Oh man, that's just, we're totally gonna overfit everything on that. Or at least we're gonna make it super big. All right. But UMAP is doing something with nearest neighbors, and I'm kind of wondering, even if you're gonna somewhat overfit on this column over here, right? We still have like 300 or something other dimensions. And it's not like in PCA where we're really just trying to, like, PCA really wants to find the most variance in a direction. That's the thing it's going to go ahead and grab. So PCA is really, really sensitive to having one column be way bigger than everything else. And what I'm wondering about UMAP is because it is in the end doing something different, if maybe there's sufficient information in all the other columns that it's able to sort of ignore the big fat elephant column in the middle there. So maybe one thing we could do. Yeah, I mean, it's hard to prove. I guess, okay, I really, I might need to ask Leland about this actually. But it does seem that UMAP is more robust. Maybe I can find some more information in the docs here. I can see some stuff about metrics. Yeah, that's all well and good. Number of epochs, learning rate, spread. There's apparently a minimum distance between embedded points. Smaller values will result in a more clustered. Whenever points closer around together, larger will alter the dispersal of points. The value should be set relative to the spread value. Yeah, there are definitely more hyperparameters around that might help mitigate this, but I don't have the greatest answer. I'm pretty happy to see that UMAP is robust against this particular instance, at least. It might be that they're doing some scaling internally, though. Like, that might honestly be a thing, but I would have to look at the source code. Okay, fine, let's have a quick look. So there's the UMAP, right? And if I sort of were to go to the fit method here, it's checking the arrays, optional argument stuff. It is doing something with k nearest neighbors. Check if we should unique the data. We've already ensured that they aren't in the pre-computed. If we aren't asking for unique in the full index, yeah. This is a long fit method, by the way. Fuzzy simplicical set. Does it say anything about scale? Yeah, scale chord such as lower is max chords than a normal distributed noise for standard event. Something is telling me that some sort of scaling is happening internally, but I need more time to properly confirm that. I also see that there is a little bit of PCA even. Yeah, so there's even a PCA thing. So I'm relatively comfortable saying there's probably something scaling something happening inside a UMAP that makes it more robust, and that's probably the reason why we see this behavior. I need to look at time. We're almost at time, by the way. This was a great question. Like, I like having being forced to do a deep dive, but I think there's some scaling happening on the UMAP side. That's probably the thing that we're seeing here. There are some questions. Agree with robustness. Needs tinkering to calibrate to make sure we've got a visual sense for our 3D, 4D minds. Yeah, so there is definitely this thing where us humans like to think in like 3 to 4 dimensions, and that can be a small bother. One thing about that, though, like one technique that I have found to be kind of useful, high plot. I think it's an archive project now, but it's still a high plot Facebook. There we go. This is an archive project now, but there's this thing called high plot. And what that does is it gives you a parallel coordinates chart. So there are like 5 or 6, I should say, columns here. And they all have different values, and you can kind of just make a sub-selection of the values if you're interested in selecting a subset. All of these axes that you see over here represent a column, and you can just make a sub-selection within that. And I have found that this visualization technique broadens your mind a little bit and makes it a little bit easier to just get an impression of what's happening beyond 2 or 3 dimensions. It's still tricky, though. This is definitely like a cool trick, but it's also kind of a rabbit hole if you're not careful. So if you're interested in like visualizing higher dimensions, I do think parallel coordinates is the way to go. Highplot is a pretty likable implementation of it, even though the library itself has been archived now. But this is a thing that I like to use a lot for grid search results. Like apparently valid PPL is like the thing we're optimizing over. Let's have a quick look. Like, what are the high values? Where do they come from? Like, it's a certain embedding size and a certain dropout value, etc. And maybe certain learning rates cause that more. And actually, maybe the embedding size matters more. And we have to have a high epoch and a low embedding size, stuff like that. Like that's stuff that you can pretty easily grasp with Highplot. Highplot is pretty cool. One dimension just means that determine the nearest neighbors. It still has all the other dimensions. PCA is used. You have to initialize the mapping. Thanks for your deep dive. Yeah, so that's my conclusion. Oh, and I'm happy to hear that this Highplot thing is something that you're definitely interested in. I maintain a little learning library called Column Code. There is a tutorial on Highplot there. If you look at my PyData Amsterdam keynote of last year, it also has a section where I dive into this Highplot tool. The only thing that's good to observe with HiPlot, I highly recommend it, but it's not actively maintained anymore. That's the main thing that you should just keep in the back of your mind. I don't think it needs extra features. It's pretty perfect as is. But like if a new operating system or new web technology comes out, don't expect this to work forever and ever and ever. Having said all that, just to go back to the Jupyter Notebook, what I do hope is that people agree this was kind of a fun exercise. Again, PCA, global structure, great for regularization. That is a really good use case. UMAP is definitely more finding clusters and figuring out a way to plot them in 2D. They still both have their use cases in visualization land, assuming your data is standardized in the case of PCA. But there is this interesting relationship between the two. Like, if you want to zoom in on the global data structure distances, then PCA definitely has a leg up, but they also have an interaction. So I think depending on what you're doing, if you're looking for interesting training data to label, there's stuff to like, that for sure. So if there's any quick questions, I will definitely take them now. If not, thanks for joining me on a Saturday. In the next few live streams, I will be doing something different. I am going to work on a single project for a couple of live streams put together. And what I'm going to be doing is I'm going to be writing a bit of PyTorch to make a new scikit-learn estimator. I'm looking for, what I'll be building is something called a mixture density network. We'll talk about what that exactly entails in the next live stream. But basically that's a system that will allow me to also, whenever I make a prediction, it will also allow me to predict the quantile. That's the main key thing that I'm interested in predicting here. So we're going to build a scikit-learn model that can do quantile estimating at runtime. And that should also allow us to dive a bit deeper into this feature of scikit-learn called metadata routing, because it allows us to make a model where we can set the quantile at prediction time, and it doesn't have to train for it up front. All sorts of like fancy deep dives we can do with all of that, so I'm happy to look forward. But what also will be cool about the live stream then is every time that I do a live stream, there will be a milestone in the GitHub repository, and everyone is sort of free and invited to collaborate. Like we can kind of build the docs together if that's something that people are interested in. Might be a fun little experiment. Something like that I think would be cool for the live stream as well. It's not just me talking, could be a little bit more collaborative. That'll be like a fun experiment. So next week I'll talk about mixture density networks and like why is that even interesting, and I'll show like a very old implementation I once wrote in TensorFlow like 6 years ago. And then the goal will be that we're going to do something more modern in PyTorch and build like a little Python package for scikit-learn, like a little scikit mixture density network plugin, so to say. If people have suggestions for a name, I'm also still in the market for that. Thanks for listening. I hope people also enjoyed the new setup I've got here with like a proper tenting ergonomic keyboard setup. Like I can really do the fancy stuff. More of that in an upcoming video. But thanks for listening, and I don't see any more questions popping up, so I'm going to hit the stop stream button. Reach out to me on socials if you have any questions, and yeah, I hope people don't mind tuning in on a Saturday, and I also hope that people enjoy the idea or the thought, at least, to work on a scikit-learn plugin during the live stream.